Alright, in this video I'm going to show you how to use what I call graph annotations to solve physics problems involving things traveling at different speeds with different accelerations. Okay? So the problem we're going to start with here is that a car starts at rest and then speeds up at a rate of 5 meters per second every second, and it does that for 10 seconds. And so the big thing we're going to focus on right here is what I mean by sketch and annotate a velocity graph and an acceleration graph. And then I'm going to show you how to use those graphs to make these two calculations here. Okay. Now it's important to remember that we take this one step at a time. So right now you don't know how to make these calculations. That's okay. The point here is to Alright, in this video I'm going to show you how to use graph, velocity and acceleration graphs to solve problems like the one you see right here. So we've got a situation where a car goes from sitting still, that's what we mean by at rest, so the car accelerates, which means that its velocity changes, from rest, and the acceleration here is 5 meters per second, and it does that for 10 seconds. And so I'm going to show you by what I mean by sketch and annotate a graph and how we can use those graphs as tools to make the calculations down here. Now the important thing to remember is that right now you have no idea how to make these calculations. That's okay. What we're going to be doing here through setting up the graphs, you're not going to know how to make these calculations until the graphs are set up and ready to go. So don't even worry about numbers 2 and 3 yet. When you're doing these kind of problems, the first thing you always do is set up your graphs, and then those will be the tools that you use to make the calculations. Okay, so I'm going to go over here to a whiteboard, and so I'm going to start by sketching a qualitative velocity versus clock reading graph. So I've drawn my axes here. I've put V for velocity, T for clock reading, and what I mean qualitative is I'm just going to draw the shape of what this graph would look like. I'm not going to worry about tick marks or numbers or anything like that yet. So if the car accelerates from rest, that means that the velocity should start here at 0, and then it speeds up at 5 meters per second every second. So that means that my velocity will start here at 0, and then the object gets faster as the clock reading increases. And that's it for now. We'll come back to this in a minute, but the next thing is that we're going to do the acceleration versus clock reading graph. Again, just qualitative for now. So A for acceleration, T for clock reading. And so here, the acceleration, we have a number for it. We're not going to worry about the number yet, but it says the acceleration is 5 meters per second every second. And so that acceleration is going to be constant, meaning that the velocity is going to change by 5 every second. So now that we've got the shapes of the graphs out, now we need to do what I mean by annotating. And so when I say annotate, I mean kind of like we're going to take notes on the graph. We're going to add some numbers and some variables here. So I go back over here, it says accelerates from rest. So I'm going to go back to my graph and say, well, that means that my initial velocity, that's an I there, V for velocity, I for initial, is equal to 0 meters per second. Okay? And I put it right here because the initial velocity is right there at the clock reading at 0. Okay? Now if I go back, it says it does this for 10 seconds. So what I'm going to do is I'm going to drop a little dotted line here just so I can see where it hits my time axis. And so let me erase this and oops. make some room. Okay. And so I'm going to write t equals 10 seconds. Okay. Go back to my problem. That's all I've got for the velocity. Okay. But I'm not done yet, because I don't know the velocity at the end of it, but I still want to give it a variable name to show that, hey, this could be important later on. So I'm just going to call it VF for final, and I'm just going to leave it there. We'll come back to it later. Okay? The last thing that we need to add on here is showing the distance traveled by this car. Now, we don't know what that distance is, but the way that we figure out how to get distance from a velocity graph is to take the area. So we'll talk about that in a minute, but right now we're just showing that, hey, if I found the area of this, it's a triangle, then that would tell me how far the car traveled. Okay, and distance here is this symbol here. That's the Greek letter delta, means change, and x position. So delta for change, x for position. So change in position, which is just a fancy physics way of saying distance. And what I'm going to do is I'm going to shade in the area here to show that my delta x, or my distance traveled, is represented by the area of this graph. Okay. Now, we're not worried about calculating it yet, but we'll come back to it. So now my velocity graph is done. I'm going to jump over to my acceleration graph. So if I go back here, I see that the acceleration is 5 meters per second. So I need to write, I'm running out of room here, but a equals 5 meters per second. Apologize, that's a little sloppy. Now if I go back over here, I need to add my time. So I'm going to drop a dashed line here to show that that's where my time is. Let me redraw my t, and t equals 10 seconds. Okay. Now, just like the area of a velocity graph means something, the area of an acceleration graph means something as well. And so what the area of an acceleration graph tells you is, there's that triangle symbol again, it just means delta, or it's the Greek letter delta that means change, and then V for velocity, so it tells you the change in velocity. Okay, and so I'm going to shade that in as well to show that, oops, let's get green, there we go, just to show that the area here, which is a rectangle, would give you the change in velocity. Okay, so now the graphs are all set up. They are set up and they're annotated. And so now we can actually start thinking about how to make these calculations. Okay, so number two, calculate the velocity of the car after 10 seconds. So we know the velocity starts at 0, but we want to know what it is at 10 seconds. So we want to know how much it changed by. It went from 0 to some other number. And so this is where we're going to use our acceleration graph. Because if we know the change in velocity, we can figure out the final. And a good way to think about what delta V is, oops, let's go back to black. So if I have my initial velocity, okay, and let's do this instead. So if we think about this as a number line, right, where my initial velocity is 0, and I've got some other tick marks here, and then my final velocity is some number here that I don't know, delta V is is the gap right there. Oops, it's not letting me draw. Let's go down a little bit. So delta V is that gap. So if I know what delta V is, I can say initial velocity plus the change, and that'll give me my final. So to get my delta V, I have to find the area of this shape, which happens to be a rectangle. So I know that the area here is going to be delta V, and since it's a rectangle, I do length times width. So the length here is going to be my time, which is 10 seconds, and the height is going to be the acceleration. So that's 5. And so when I do that, I get 50 meters per second. And so that tells me that this delta V up here, so from VI to VF, is a change of 50. So 0 plus 50 equals 50. Let me make some room over here. So I have VF equals 50. Okay. So there's the velocity of the car after 10 seconds. The next thing is that we got to calculate the distance the car travels. Okay? And so the distance that a car travels, again, that's that delta x variable, which is represented as the area of this triangle here. So I know that the area of a triangle, okay, which would give us delta x, is 1/2 base times height, again, because it is a triangle. Oops, that got a little messed up. Height. Oops. Now, if I want to calculate this area, I figure out the base and the height. So the base here, like in the other one, is 10 seconds. And then the height is that velocity, that final velocity right there, so 50. And then if I calculate that out, 10 times 5 is 500, divided by 2 is 250 meters. So this tells us that the car, while it's accelerating from 0 meters per second to 50 meters per second, that it travels a distance of 250 meters. Let's draw that a little cleaner. Okay. So this is a very basic example of sketching and annotating a velocity and an acceleration graph, and then how to use that graph to make some calculations. The next video, I'll show you a little more complicated example so you can see all the different things you can do.